So this is number 18 from section 6, which is on integration by parts. And so far, the most powerful tool that we have for handling complex integrals is the substitution rule. But sometimes the substitution rule isn't enough. So, like for example, in a case like this, if you started to use the substitution rule, you would run into a dead end. It's not powerful enough to actually solve this problem. So, if you were to try to let u equal natural log y, then du would be 1 over y, which we don't have, dy, excuse me, which we don't have in here to, we don't have a way to represent that and do a direct substitution. So setting u equals natural log y didn't work. So let's try it the other way. Let's let u equal to, u is equal to y to the 1/2, well du would be 1/2 y to the negative 1/2 dy, and there's nothing even close to that. So the substitution rule won't work in this case. We need a more powerful tool. And the more powerful tool for handling complex integrations is called integrations by parts. And basically, integration by parts says that when you have something like a product, for example, this can be rewritten as natural log y times 1 over square root of y dy. If you're trying to anti-differentiate a product, then naturally you're going to be doing some kind of, then you start with the product rule, you anti-differentiate the product rule and see what tools fall out that can be useful. So basically the product rule says f times g. If we were to take the derivative of that, dx of fg, that's going to be f prime times g plus g prime times f. Well, if we wanted to find the antiderivative of that, then what we have then is f times g is equal to the integral of f prime times g plus the integral of f times g prime. So, if I want to solve for that, I'm going to move this over here and say that the integral of f prime times g is equal to fg minus the integral of f times g prime. So we simply replace f and g with u and v, and that says that the, I wanted to move fg prime. I want to move, okay, it's just a matter of which one is called a prime, but to be consistent with the book, I should have moved this one over, so that, just to be consistent with the book, so I have f minus fg prime over here, fg prime to f prime g. Okay, so that says that the integral of u dv, if I let u equal f and g is equal to v, then the integral of u dv is equal to u times v minus the v du. So that is integrations by parts, how we'll do it. We're going to re-identify each part of this as either a u or a v. Take the product of it, subtract the integral of our v and then our du, and our goal is to have a simpler function to integrate, and hopefully that we don't have to employ other tools like the substitution rule. But okay, so now we have a tool that we can use to try and anti-differentiate that. So if you take a look at this, the first thing you have to do is decide which part of this will be u and which part of this will be dv. You can think about it this way. If the integral of u dv is equal to uv minus the integral of v du, if we pick some kind of v that we can't easily differentiate, then we might make our problem even more complicated. So if there's any component of your integral that is actually hard to anti-differentiate, then we should set that to be the u, because if it's easy to find the differential of that, then we want to definitely set that as a u. And that's the case here, because the natural log of natural log of y really lends itself to be defined as u, because we don't have an easy way to do that. What's the integral of that? It's not easy to solve. In fact, it's solved by using integration by parts. So, so if we set that to be u, if we let u equal natural log of y, du is really easy to find. We know that to be 1 over y. So it really lends itself to be defined as u. But if you didn't know that and that wasn't obvious, and you started to work out that, and you get to this step where you have to do the integral of v, and you're like, okay, if that didn't work, you just go back and swap it around and try it with the other way. So, we're going to let u be the natural log of y, then du is 1 over y dy. If this is du, then this is dv, right? So dv is, we're going to call this y to the negative 1/2 dy, because it's easier to do the integral of that. So to find v, we differentiate both sides. V then is going to be y to the 1/2 over 1/2, and that is equal to 2 square root of y. Now we plug it into our integration by parts formula that says the integral of u dv is equal to uv minus the integral of v du. So what's u and v? U is the natural log of y, and v is 2 root y, minus the integral of v, which is 2 square root of y, du, which is times 1 over y dy. So this is much easier to solve than what we originally had. So now, this was a definite integral, so we're evaluating from 4 to 9. So we have here 2 root y, natural log of y, minus, this is going to become the integral of root y over y of 2 over root y dy. I'm going to rewrite that as 2 root y, natural log of y, minus the integral of 2y to the negative 1/2 dy. That is equal to 2 root y, natural log of y, minus 2y to the 1/2 over 1/2. That is equal to 2 root y, natural log of y, minus 4 square root of y. And we evaluate that from 9, the interval of 9 to 4. Okay, so what do we get when we evaluate that? Evaluate at 9, we have 2 root 9, natural log of 9, minus 4 root 9, minus 4 root 4, minus 4, minus 2 root 4, natural log of 4, minus 4 root 4. That gives us 2, this is root 9 is 3, so that gives us 6, natural log of 9. Root 9 is 3, so 4 times 3 is minus 12, minus 2 times 2 is 4, so this gives us 4, natural log of 4, minus 4 times 2, which is 8. And we have 6 natural log of 9 minus 12 minus 4 natural log of 4 plus 8. And that reduces to 6 natural log of 9 minus 4 natural log of 4 minus 4. And that is the answer to problem 5.6.18. And natural log 9, 4 natural log 4 minus 4. Okay, cool. Drop me an email if you have questions. Thanks.